Welcome to a fascinating journey into the cutting edge of materials science. Today, we're exploring a groundbreaking innovation that combines the ancient strength of spider silk with the modern marvel of graphene. Researchers at the University of Tsukuba and at Zurich have created a biohybrid material that could revolutionize everything from medical implants to renewable energy. This isn't just another incremental advance. It represents a fundamental shift in how we create high-performance materials, potentially solving one of the greatest challenges in modern materials: creating products that are simultaneously ultra-strong, lightweight, and environmentally responsible. In a paper published last month in the Journal of Advanced Biomaterials, scientists achieved what many thought impossible, successfully combining recombinant spider silk proteins with graphene nanosheets to create a composite material with extraordinary properties. This unlikely pairing has produced a material that surpasses both natural spider silk and conventional graphene-based materials in strength and flexibility, while maintaining critical biological compatibility and biodegradability. The convergence of these seemingly unrelated fields, biological protein engineering and carbon-based nanotechnology, marks a paradigm shift in materials science that could transform industries from medicine to renewable energy technologies. The team behind this innovation was led by Dr. Hiroshi Miyamoto and Dr. Elsa Weiss, who brought together expertise from multiple scientific disciplines. Their approach exemplifies modern scientific collaboration at its best. Using CRISPR-Cas9 gene editing technology, they modified the genome of Bombyx mori silkworms, enabling these common silk producers to create a modified version of the dragline silk protein normally found in Nephila clavipes, the golden orb weaver spider known for producing some of the strongest silk in nature. The modified proteins were then extracted and combined with graphene oxide sheets using a novel self-assembly process in an ionic liquid medium. This interdisciplinary approach, combining genetic engineering, protein chemistry, and nanomaterials science, demonstrates how the traditional boundaries between scientific disciplines are increasingly dissolving in 21st century research. The properties of this new biohybrid material have stunned the scientific community. With a tensile strength of 2.1 gigapascals and a toughness of 418 megajoules per cubic meter, the graphene-enhanced spider silk exceeds the performance of Kevlar by approximately 35% while weighing significantly less. To put this in perspective, a thread of this material the thickness of a pencil could theoretically lift several cars. But perhaps most surprising is the emergence of piezoelectric properties, the ability to generate electricity when mechanically deformed, a characteristic present in neither spider silk nor graphene alone. As Dr. Weiss explained, what we're observing is an emergent property arising from the specific molecular interactions between the spider silk's beta sheet nanocrystals and the graphene oxide sheets. The hierarchical structure creates a synergistic effect we hadn't anticipated. This phenomenon illustrates a central principle in materials science. The arrangement and interaction of components at the nanoscale can produce macroscale properties impossible to achieve through simple mixing or blending of materials. Unlike previous attempts at creating high-performance composites, this material maintains biodegradability, decomposing by approximately 89% within just 120 days in simulated soil conditions. This represents a potential solution to one of the most persistent challenges in advanced materials science: creating high-performance materials that don't persist indefinitely in the environment. Detailed spectroscopic analyses reveal that soil microorganisms can metabolize the silk protein component, which subsequently weakens the graphene network's structural integrity, allowing for further decomposition. Environmental toxicologist Dr. Maria Rodriguez from the University of Barcelona has conducted preliminary ecotoxicity assessments and found particularly encouraging results. The biodegradation pathway doesn't release free graphene nanosheets into the environment. The silk proteins essentially wrap and contain the graphene components during breakdown, minimizing exposure to soil organisms, she reports. Her mesocosm studies suggest minimal impact on soil microbial communities at expected disposal concentrations, addressing critical concerns about nanomaterials' potential environmental persistence and unknown ecological effects. The material also demonstrates remarkable thermal resilience, maintaining its mechanical properties across an impressive temperature range from -40 degrees to +180 degrees Celsius. This thermal stability, highly unusual for biological materials, is attributed to the unique cross-linking mechanism between the silk proteins and graphene sheets, creating a thermally stable network while preserving flexibility. According to Dr. Miyamoto, The hydrogen bonding network between the protein's amide groups and the oxygen-containing functional groups on the graphene oxide creates a dynamic scaffolding that can absorb thermal energy without compromising structural integrity. This property makes the material suitable for applications in extreme environments where conventional biomaterials would fail, from Arctic conditions to high-temperature industrial settings. The research team has already identified several promising near-term applications for their biohybrid material. Swedish textile manufacturer Trelleborg AB has partnered with the researchers to explore scaled production for use in medical sutures and specialized protective clothing. The material's extraordinary strength, flexibility, and biocompatibility make it particularly promising for medical applications where current materials force compromises. Surgical sutures made from this material could potentially handle greater tension while causing less tissue reaction and naturally biodegrading at an appropriate rate. For protective clothing, the material could provide enhanced protection against impacts, cuts, and extreme temperatures while remaining lightweight and comfortable, a combination previously unachievable with conventional materials. One of the most unexpected applications comes from the material's piezoelectric properties. The graphene-enhanced spider silk generates small electrical currents when subjected to mechanical deformation, essentially converting movement into electricity. While the power output remains modest, preliminary tests suggest exciting applications in self-powered biosensors and wearable health monitors that wouldn't require external power sources or battery changes. Imagine a heart monitor patch that powers itself from the patient's chest movements, or environmental sensors that can operate indefinitely using only wind vibration. This capability addresses a significant limitation in current wearable technology: the need for regular battery replacement or charging. Dr. Akiko Tanaka, a biomedical engineer at Osaka University who wasn't involved in the original research, has begun exploring perhaps the most futuristic potential for the material: neural interfaces. The combination of electrical conductivity, mechanical flexibility, and biocompatibility makes this an ideal candidate for next-generation neural electrodes, she explains. Current materials force us to choose between good electrical properties and biocompatibility, but this hybrid material potentially offers both. Her laboratory has initiated preliminary biocompatibility studies using neural stem cell cultures, with promising early results showing normal cell adhesion and differentiation on the material's surface. This could eventually lead to improved brain-computer interfaces, spinal cord injury treatments, and neural prosthetics that integrate more effectively with human tissue while providing superior electrical connectivity. Despite its promising properties, significant challenges remain before this material reaches widespread commercial use. Scalability of production represents the most immediate hurdle. Currently, the team can produce only several square centimeters of the material per batch, using laboratory-scale bioreactors and specialized equipment. Dr. Weiss acknowledges this limitation. We're actively working on process optimization to increase yield while maintaining quality. The involvement of industrial partners like Trelleborg has been invaluable in identifying the engineering challenges we need to overcome for commercial viability. The complex production process requires precise control of multiple biological and chemical parameters simultaneously, a significant engineering challenge when moving from laboratory to industrial scale. Additionally, the specialized equipment and expertise required currently result in high production costs that would need to be addressed for mass-market applications. Beyond its initial production and use, the research team has demonstrated promising circular economy applications. Their studies show that up to 70% of the graphene component can be recovered from degraded material and reincorporated into new batches, significantly reducing the material's environmental footprint and addressing resource concerns. This recyclability directly addresses a critical concern with nanomaterials: their potential environmental persistence and unknown ecological effects. The recovery process involves a specialized enzymatic treatment that preserves the graphene structure while breaking down the protein components, allowing for separation and reuse. This approach could potentially create a closed-loop system where end-of-life products become raw material for new production, dramatically reducing waste and resource consumption compared to conventional advanced materials. This development represents more than just another incremental advance in material science. It signals a fundamental shift in how researchers approach the creation of high-performance materials. Rather than relying solely on petroleum-based polymers or energy-intensive metallurgical processes, this biohybrid approach harnesses billions of years of evolutionary refinement combined with cutting-edge nanotechnology. Dr. Miyamoto emphasized this broader significance. We're witnessing the emergence of a new paradigm in materials science. Instead of forcing nature to conform to our industrial processes, we're adapting our processes to work with nature's sophisticated molecular machinery. This philosophical shift, viewing biological systems not just as inspiration but as active components in next-generation materials, could transform how we approach everything from product design to manufacturing processes. The interdisciplinary nature of this breakthrough underscores the importance of collaborative research spanning traditional boundaries. As Dr. Weiss reflects, this work would have been impossible even 5 years ago, before advances in gene editing, protein expression systems, and nanomaterial characterization all reached sufficient maturity. It's the convergence of these separate fields that enabled our discovery. The marriage of spider silk and graphene represents a watershed moment in materials science, one that challenges our fundamental approach to creating advanced materials. By combining nature's sophisticated molecular machinery with cutting-edge nanotechnology, researchers have created something greater than the sum of its parts, a material that is simultaneously super strong, lightweight, electrically conductive, biodegradable, and biocompatible. This breakthrough demonstrates that we no longer need to choose between high performance and environmental responsibility. As this technology moves toward commercialization, it offers solutions to some of our most pressing challenges in medicine, energy, and sustainable manufacturing. The graphene-enhanced spider silk composite is likely just the beginning of a new generation of biohybrid materials that will help resolve the seemingly contradictory demands for advanced technological capabilities and environmental sustainability. In this new chapter of materials science, written in the language of both biology and nanotechnology, we may find answers to questions we've been struggling with for decades: how to create the materials of tomorrow without compromising the planet's future. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.